Hi there and welcome to another video for the Edexcel Further Pure 1 Math syllabus. In this video we're doing sum of series and the past paper questions on those. As always, try the question, pause the video and then mark your work against mine. Let's start. So, in this question we need to show that this sum is equal to this and we need to hence evaluate this. Now we don't use induction here, we can use the rules that we should know. Now there are a couple of things. You should learn that the sum from r is 1 to n of 1, you add the number 1 up n times, is n. You need to know that. You also need to know that the sum from r is 1 to n of r is a half n plus 1. You are given in the formula booklet the following: the sum from r is 1 to n of r squared, which is a 6th n plus 1, 2n plus 1, and you are given the sum from r is 1 to n of r cubed, which is a quarter n squared n plus 1 squared. Okay, so we're going to use these results. So let's go ahead straight away and do that with part A. So we're summing this up. That can be written as the sum of r squared, subtract the sum of r, subtract the sum of 1. And all of these obviously between 1 and n. And we're dealing with the left hand side here, let's say, the left hand side. Now, we can use our formulas for these. This one here, well, we said it's a 6th n plus 1, 2n plus 1. This sum here is subtract a half n plus 1, and the last sum here would be subtract n. Okay, at this stage, what you need to do is try and factorise. Do not expand out. Students try and expand out here, get cubics with fractions, and it goes horribly wrong. What you do is you need to factorise. You need to spot that there is an n here, an n here, and an n here. And you need to factorise out that n. Next thing, always try and factorise out the smallest fraction, or the fraction with the largest denominator. So I'm going to divide out 1/6. I'm going to factorise out 1/6. What would be left in this first section here? Well, a 6th n, I've divided that out, so I'd be left with n plus 1, 2n plus 1. Subtract. Now a half divided by a 6 is 3. The n has been factorised out, so I'd be left with 3n plus 1. And here the n's gone, and 1 divided by 6 is 6, so I'd have to subtract 6. Now, and only now, do I consider factorising and collecting like terms. If you're ever expanding out a cubic when doing these, you are in the wrong, you have not done appropriate factorisation. But when you get down to a quadratic, you should be fine. So 6 then, this factorises out to, this expands out to 2n plus 1 squared plus 3n plus 1. This expands out to subtract 3n, subtract 3, and this is subtract 6. Tidying that all up, you would have 2n squared, the n's go, and you would have subtract 8. Then you could factorise out a 2, because there is a 2 in both these, so that would be 2 6, which is a third, n, and you'd have n squared subtract 4, and then notice that's a difference of 2 squares, so that factorises as n subtract 2, n plus 2. And conventionally, you just let the smallest bracket be first, so this would be equal to a third, n subtract 2, n plus 2, and you've got yourself a very straightforward 6 marks. Part B, hence evaluate this. Well, you want to work out the sum from r is 10 to 40 of r squared subtract r subtract 1. Now, you have a formula to work these sorts of things out now, but looking back, the formula only works when r is 1. So what we're going to do is we're going to break this sum up from r is 1 to 40 of r squared subtract r subtract 1. and we're going to subtract off r is 1 to 9 of r squared, subtract r, subtract 1. That would leave us between 10 and 40. Now it's handy to write it like this, is we have a formula for this and a formula for this. And the formula is given in part A, a third n minus 2 n plus 2. So here I can work this out by doing a third, n minus 2, which would be 40 minus 2 is 38, n, which would be 40, and then n plus 2, which would be 42. And we're going to subtract off a third, and here our n is 9, so n minus 2 is 7, n is 9, and n plus 2 is 11. And all we have to do is tap that in our calculator and check we've got the right answer. So just tapping that in the calculator, should have ourselves the answer 21,049, and we're done for 3 more easy, straightforward marks. Next question. Okay, part A, we want to prove the following by induction. So, our proposition, step 1, let's write down what we're trying to prove. Our proposition. Well, our proposition is just stating this fact. We're trying to show that the sum from r is 1 to n of r squared is a 6th n plus 1 to n plus 1. And the very first thing we do in an induction, the next thing we do is we check it's true in the basis case. And the basis case in this time is for n is equal to 1. So on the left hand side, we would have the sum from r is 1 to 1 of r squared, which is just 1 squared, which is simply 1. On the right hand side, we would have a 6th, 1, 1 plus 1 is 2, and 2n plus 1 is 3. And that is also equal to 1. Therefore, proposition is true. For n equal 1. Okay, the third step is to assume, is the assumption step, is to assume true for n equals k. And by that, I write down what you mean. You're meaning you're assuming that the sum from r is 1 to n is k, so to k now, of r squared is 1/6 k, k plus 1 to k plus 1. Okay, that's our assumption. Now I'm going to do a little bubble over here to show what we're trying to find. We are trying to show this is going to be true in the k plus 1 case. We are trying to show that the sum from r is 1 to k plus 1 of r squared turns out to be 1/6. If that was a k plus 1, it would be k plus 1. If that was k plus 1, this would be k plus 2. And if that was a k plus 1, we'd have 2 times k plus 1 plus 1, which would be 2k plus 3. That's what we're trying to show. Okay, we are trying to show that. We can't just write that down. We're trying to demonstrate that that is the case using our knowledge of the sum and our assumption step. So just take a minute now to just make sure you've got this down. I'm going to rub this out and I'm going to keep going from part 3 here. Okay, rubbing this out then. Actually, what might be handy is if I just keep that here. Might be just handy to keep that in there. Okay, just to show where we're trying to get to. Right. So, the next step 4, which is the inductive step. We're trying to work out this sum, so let's just write it down. We're trying to work out the sum from r is 1 to k plus 1 of r squared. We're trying to show it equals this. So the only thing we can do is, why don't we just break this sum up between r is 1 and k of r squared, and then we'll break that up because we know what this is from the inductive step, and then we'd have the k plus 1th term, which is what happens when you sub k plus 1 in here, and you get k plus 1 squared. So from the assumption step, this is equal to a 6th k plus 1, 2k plus 1, and we'd have our plus k plus 1 squared. Okay, so again, at this stage, if we're trying to deal with something like this, don't start expanding out. You will get a cubic with fractions. Factorise first. Notice there's a k plus 1 here and a k plus 1 squared here. So let's factorise out a k plus 1. Also take out the smallest fraction, or the fraction with the, divide out the smallest fraction, or the fraction with the largest denominator. So divide out a 6th. Then over here we would be left with the 6 is divided out, a k plus 1 is divided out. We would be left with k, 2k plus 1. And here we'd be left with a k plus 1 left, but also we've divided out a 6th, so that's the same effect as multiplying 6. Right, so we'd have a 6th k plus 1. Expanding this out, we'd have 2k squared plus k plus 6k plus 6. Just collecting like terms, that would be a 6th k plus 1, 2k squared plus 7k plus 6, and then factorising that, we get exactly what we're looking for then. It would factorise out as k plus 2, 2k plus 3, and we'd be done then. We've finished and we've got the answer we're looking for. And then step 5, don't forget step 5, you need to therefore say, therefore true for n equal 1 and n equal k and n equal k plus 1, therefore true for all n bigger than or equal to 1. And you're done. Next part, it says using standard results show that the following is true where a and b are integers to be found. So we're trying to work out this sum here. So this is the same as working out the sum of, if we expand this bracket here, the sum between r is 1 and n of r squared plus 5r plus 6, which if we break it down is the sum of between r is 1 and n of r squared plus 5 lots of the sum from r is 1 to n of r plus 6 lots of the sum from r is 1 to n of 1. And we can use standard results. The sum of r squared, well, that's a 6th, okay? Just shown this over in this part here. That's a 6th, n plus 1, 2n plus 1, plus 5. This sum here is a half, so it would be times a half, n plus 1. And this here, this sum is simply n, so plus 6n. Now, at this stage, again, do not try and multiply out. You will get cubics with fractions. It will be a nightmare. Firstly, see if you can factorise. N here, n here, n here. Very sensible, and is a requirement, really, to factorise out that n. Then take out or divide out the smallest fraction. So take out a 6. What are you left with? Well, here, you're left with n plus 1, 2n plus 1. Here, well, this here is 5 over 2. So if you do 5 over 2 in your calculator, divided by 1/6, you get yourself 15. So this would be plus 15. The n's divided out, so you'd have n plus 1. And here the n's gone, but you do 6 divided by 6, which is the same as 6 times 6, which is 36. So, you'd have a 6 then, 2n squared plus 3n plus 1 plus 15n plus 15 plus 36. And now it's just collect the like terms game. you'd have a 6n. Here you'd have 2n squared, and you'd have that and that is 18n, and that and that and that is 52, plus 52. Lastly, you could take a factor of 2 out from here, so 2 6 would be a third n, and you'd have n squared plus 9n plus 26. And what is your a and your b? Well, your a is 9 and your b is equal to 26, and we're done. Part C, hence show that the following is true. Well, I have just worked out some expression for this on the previous part here. It's that. However, that's the sum between 1 and n. So here, we are trying to deal with the sum from r is n plus 1 to 2n of r plus 2, r plus 3. So break it up. Break it up into the sum from r is 1 to 2n of r plus 2, r plus 3. But we've overcounted between 1 and n, so subtract the sum between r is 1 and n of r plus 2, r plus 3. Now we have formulas to use these. Remember our formula from the previous page? It's a third n squared plus 9n plus 26. So it's a third n squared plus 9n plus 26. That is our formula for the sum from 1 to n. Here's the sum from 1 to 2n. So we have a third 2n squared plus 9 times 2n plus 26. Subtract this, which the sum from 1 to n is a third n squared plus 9n plus 26. Okay, before we launch into anything complicated here, factorise out a third and factorise out an n maybe. Factorise out a third and an n. And then in here we'd be left with that 2 multiplied by everything in here. So it'd be 2, and just multiplying this out, 4n squared plus 18n plus 26. And then subtract n squared plus 9n plus 26. So let's multiply this out. This would be 8n squared plus 36n plus 52, and all of that subtract n squared plus 9n plus 26. And then if we do the subtraction, we have a third n, 8n squared minus n squared is 7n squared, 36 subtract 9 is plus 27n, and 52 subtract 26 is plus 26. And we'd have the answer we're looking for, and we're done. Okay, next question. Right, we want to show using these formulas that the following is true. Here, that should have been a times there. So, let's do that. Let's break this sum up here. So the left-hand side, let's break that up as the sum from r is 1 to n. 6 lots of the sum of r squared plus 4 lots of the sum of r, subtract 1 lot of the sum of 1. Okay, let's use standard results. This one here is 6. Now this result here is in the formula booklet. It's a 6th n plus 1, 2n plus 1. This one here is 4. This here should be a half n plus 1. And lastly, this is just n, so subtract n. Now, just multiply the numbers just to tidy it up before we do anything. So this would be n 6 times a 6 would just be 1. So n plus 1, 2n plus 1. 4 times a half is 2, so plus 2n plus 1, and then subtract n. Now, before you start multiplying out and having cubics to deal with, factorise. N there, and n there. So factorise out the factor of n, and you'd be left with n plus 1, 2n plus 1, plus 2 multiplied by n plus 1, subtract 1. Now it's easy to multiply this out. So now multiply this out and gather. So you'd have 2n squared plus 3n plus 1 plus 2n plus 2, subtract 1. So you'd have n 2n squared plus 5n plus 2, and therefore n, that would be n 2n plus 1 n plus 2. Simple as that, and you're done. You've got the result you wanted for 5 marks. Hence or otherwise, find the value of this sum. Well, clearly this sum, the sum from r is 11 here, not 1 to 20, of 6r squared plus 4r subtract 1. Well, if I want to work that sum out, I want to use the result in part A, but the result in part A starts when the sum is 1. So I need to break this sum up as a sum from r is 1 to 20 of 6r squared plus 4r subtract 1. And I've overcounted the sum from r is 1 up to 10. So I'm going to subtract off the sum from r is 1 to 10 of 6r squared plus 4r subtract 1. Okay? So I've got a formula for these sums from part B. It's n plus 2, 2n plus 1. So this is going to be, remember our formula here, that I'll just write it down so we don't make a mistake. So for whatever our n is, what we're summing to is n plus 2, 2n plus 1. Okay, so what we're going to do is we're going to sub in n is 20 here. So it'd be 20 times 22 times 41, subtract 10 times 12 times 21. And all you have to do is tap that in your calculator, and you get yourself 15,520, and then you'd be done. You can also check this on the calculator by using the sum function and sum from 11 to 20 on your calculator of 6x squared. Same thing, it lets you do it in the calculator, plus 4x subtract 1, and if you tap that in your calculator you do get the same thing. It's very worthwhile checking that, although you have to show your workings in the exam, but it's good to check that on our Casio FX991ES Plus, which does that for us. Okay, next question. We want to prove that the following is true. Okay, now there are different ways to prove this. We could prove this by induction, or we could prove this by using standard results. Let's just do the standard results one. If I multiply that out here, I'd have the sum from r is 1 to n. If I multiply this out, I would get r squared plus r subtract 2, which is the sum from r is 1 to n of r squared, plus the sum from r is 1 to n of r, subtract 2 lots, the sum from r is 1 to n of 1. Using standard results, so 6n n plus 1, 2n plus 1, plus a half n n plus 1, subtract 2n. Now at this point, before you multiply out, realise there's an n that can be factorised, so factorise out an n, and the smallest fraction, which is a 6. Doing that, in the first instance here, you get n plus 1, 2n plus 1 left. Here, a half divided by 6 is 3, so you have 3n plus 1. And here, 2 divided by 6 is 12, so you'd have subtract 12. So keeping going with this, now it's time to multiply out. If you multiply out, you get 2n squared plus 3n plus 1 plus 3n plus 3 minus 12. And you'd have a 6 then, 2n squared plus 6n subtract 8. You could factorise out a 2 from that, because there's a 2 here, 2 here, and 2 here. So you'd have 2, 6, which is a third, n squared plus 3n subtract 4, and if you To factorise that, you'd have a third n plus 4, n subtract 1, and you've got the result you're looking for at the top. So we're done. Next question, show that the following is true, hence evaluate this. Same old sort of stuff. So for part A, let's just expand out the r plus 1, r plus 5. So that would be the sum of r squared plus 6r plus 5. And you could break that down as the sum from r is 1 to n of r squared plus 6 lots of the sum from r is 1 to n of r plus 5 lots of the sum from r is 1 to n. Okay, so this here, well, this is a 6th n plus 1 to n plus 1. This here, well, this is a half n plus 1, times that by 6, so you'd have 3 n plus 1, and here you'd have plus 5n. Before, again, you multiply out. There's a 5 here, an n here, an n here, and an n here. So make sure you factorise out an n. Also take the smallest fraction out, or factorise out the fraction with the largest denominator. So factorise out a 6. Also do that because you see it in the answer. Factorising this as 6 then, out here you'd be left with n plus 1 to n plus 1. The n's gone here, and you'd be left with n plus 1. But 3 divided by a 6 is 18. And here the n's gone, but 5 divided by 6 is 30. Don't forget to do those steps. So we'd have a 6th n, so you'd have 2n squared plus 3n plus 1 plus 18n plus 18 plus 30. Now it's time to collect up. So 6th n, you'd have 2n squared plus 21n, and then plus 49, and so that would be a 6th n, and if you factorise that, 2n plus 7, n plus 7, and you're done. You've got the result you wanted for 4 marks. Part B, hence calculate the following. Well, the following, if you simply split this sum up from r is 1 to 40 of r plus 1, r plus 5, and you subtract away the sum from r is 1 to 9, because that's what you've overcounted, of r plus 1 to r plus 5, well then you could use the formula that you've worked out on the previous page, which is a 6n, n plus 7, 2n plus 7. So I'm going to write a 6th n, n plus 7, 2n plus 7. That's the sum from 1 to n. Here's the sum from 1 to 40, so it's a 6th, 40, 47, multiplied by 2n plus 7, which would be 87, and then subtract a 6. Well, the sum from 1 to 9 here, n is 9, so it would be multiplied by 9, multiplied by 9 plus 7, which is 16, multiplied by 2 times 9, which is 18, plus 7, which is 25. Do be very careful not to substitute the 9 in here, or the 14 here. That's what some people do, and it's wrong. And so just make sure you work that out. So it's a 6, 40 times 47 times 87, subtract 9 times 16 times 25, and you get yourself 26,660. You could also obviously make sure you do that sum on your calculator just to make sure you haven't made any mistakes at all, and that's a handy thing to do. So I'm just going to do that right now. I'm summing x plus 1 times x plus 5, and I'm doing that between x is 10 and x is equal to 40, and indeed I get the same thing, so I know I'm definitely right. Okay, next question. Now, prove by induction the following is true. Just for this here, I'm not going to do the proposition, which is stating out or checking it's true in the basis case. I'm just going to, or the conclusion step. So I'm going to just, here, I'm going to assume that we all know how to do the step 1, write the proposition. Step 2, check the basis case. And finally, the final step, which would have been step 5, is to make the conclusion. So I'm not going to go through those because I'm doing those in the induction video and I've done them many times before. So here all I'm going to do is I'm going to do the assumption step and the inductive step. So the assumption step, that says that I'm assuming the proposition is true for n is k. So assume true for n equal k, i.e. this sum is true for when n is k, i.e. the sum from r is 1 to k of r cubed is equal to a quarter k squared, k plus 1 squared. Now what I'm trying to show, in an ideal world, this is what I'm trying to show. And I'll write this over here. I'm trying to show this is true for for k plus 1. So I'm trying to show the sum from r to k plus 1 of r cubed is actually a quarter k plus 1 squared, k plus 1 plus 1, which is k plus 2 squared. That's what I'm trying to show. But I can't just write it down. I have to use my assumption step and the definition of the sum to do that. So, part 4. If I'm trying to work out the sum from r is 1 to k plus 1 of r cubed, I can break that down into a sum from r is 1 to k of r cubed, because I know that from the assumption step, plus the k plus 1 term. What happens when I put k plus 1 in here and I get k plus 1 cubed? Now, by the assumption step, this here is equal to a quarter k squared, k plus 1 squared, and we have plus k plus 1 cubed. Now I can deal with this because I could try and combine these. I could factorise first. I've got k plus 1 squared and a k plus 1 cubed here. So I'm going to factorise out a k plus 1 squared. I'm also going to take out a factor of a quarter. Okay, and here I'd be left with k squared, and here I'd be left with 4 times k plus 1. Okay, and then I'm run out of space here, but this would be a quarter k plus 1 squared, k squared plus 4k plus 1, which factorizes to k plus plus 4 there, k plus 2 squared, which is what I was after. And then make sure you go ahead and do the conclusion step. Part B, using these formula, show that the following is true. Well, you can break this up into the sum of r cubed plus 3 lots of the sum of r plus 2 lots of the sum of 1. And you can use standard results. The sum of r cubed is 1/4 n squared n plus 1 squared plus 3 times the sum of this. Well, that is a half n plus 1, so this would be 3 over 2 n plus 1, and here this would be 2 times n. So before you launch ahead, there's an n there, an n there, and an n there, so factorise out an n. Also take the smallest fraction, which is a quarter. So you'd be left with here n plus 1 squared. Here, 3 over 2 divided by a quarter, you'd have 6. So you'd have plus 6 n plus 1, and here 2 divided by a quarter is 8. Okay, so let's multiply that out now. You'd have a quarter n, and you'd have yourself here n multiplied by n squared plus 2n plus 1 plus 6n plus 6 plus 8. And if I multiply that out here, I would get n cubed plus 2n squared plus n. Well, I have a 6n, so I'd have plus 7n, and 6 and 8 is 14. Okay, now I know this factorizes out because I know here that it must factorize like that. So all I've got to do is try and take out a factor of n plus 2. What do I need here to times by n to get n cubed? Well, an n squared. That gives me 2n squared. I want that, which is good. And what do I need here to get me the 7n? So I need plus 7. That times that gives me 7n. And that times that gives me the 14. Hence I'm done. Simple as that. And hence evaluate the following. Well, this here, you could break it as the sum from R is 15, the sum from R is 15 to 25 of R cubed plus 3R plus 2 is simply, you break it up into the sum from 1 to 25 of R cubed plus 3R plus 2, subtract the sum from R is 1 to 14 of R cubed plus 3R plus 2. And you've got formulas for the sum of 1 from the previous. It's a quarter n, n plus 2, n squared plus 7. So it's a quarter n, n plus 2, n squared plus 7. The sum from 1 to n, that is. So the sum from 1 to 25 is a quarter, 25, 27, and 25 squared plus 7. Subtract a quarter, the sum from 1 to 14, 14, 16, 14 squared plus 7. So all you've got to do is tap that in your calculator. And you get yourself 95,282. And again, if you just wanted to check that sum function on your calculator works, it is very useful to do that just to make sure you haven't made a mistake. So I'm summing x cubed plus 3x plus 2 from x is equal to 15 to 25. Let your calculator do that, and indeed I got 95,282, and I know I'm done. Question. Using the formulae for these show that the following is true. So all we've got to do for the first part is write this sum as an expansion. So firstly, you're just going to expand this bit here, be r squared plus r multiplied by r plus 3, and then just carefully multiplying this out, making sure you don't make any mistakes. If I multiply this out, I get r cubed plus 3r squared plus another r squared plus 3r. So this would come to the sum from r is 1 to n of r cubed plus 4r squared plus 3r, which if we then break it up, that's the sum of r cubed plus 4 times the sum of r squared plus 3 times the sum of r, all between r is 1 and n, r is 1 and n, r is 1 and n. Now at this stage we can use standard results. So I'm going to say that's equal to a quarter n squared n plus 1 squared plus this is a sixth n n plus 1 over 2, and 4 times a sixth is 2/3, so 2/3 n plus 1 2n plus 1, and this here is a half n plus 1, so 3 times that will be 3 over 2 n plus 1. Okay, now just pause and make sure you've copied that down. I'm going to rub that out and move it up the page a little. So I'm going to just take this here . I'm going to move this up the page here. This is where we got to. Okay, now before you try and multiply out, notice it's got an n here, an n here, and an n here. It's also got n plus 1 here, n plus 1 here, n plus 1 here. So let's do a bit of factorising before we dare multiply out, because it would be a total mess. So factorise out an n and an n plus 1. Also the smallest fraction. Now in this case it's not always the smallest fraction, it's the smallest fraction that you know, or the smallest fraction that you know 4, 3 and 2 go into. The biggest denominator that 4, 3 and 2 go into. Now we know for sure they all go into 12, and also we've got a 12th here in the answer, so let's divide out a 12th. Now a quarter divided by 12 is 3, so we'd have 3, and we'd have an n and an n plus 1 left. 2/3 divided by 12, a 12th, we'd get ourselves 8, so we'd have plus 8
2n plus 1, and 3 over 2 divided by 12, you get 18, so you have plus 18 here. Now it's time to multiply out. We should be able to do that. Just notice in the answer here that we're trying to get to, we've got our 12, we've got our n and our n plus 1, we're looking for the rest now. So we'd have, multiplying this out, 3n squared plus 3n plus 16n plus 8 plus 18, and that would be a 12th n plus 1, and we'd have ourselves 3n squared plus 19n plus 26. Now, I also know from here that n plus 2 is a factor, so I know I should be able to factorise out n plus 2. Okay, what needs to go here to multiply by this n to get 3n squared, or 3n? 3n times 2 is 6n, I need 19n, so I need another 13, okay? So I need another 13, so just to go that again, 3n squared gives me what I'm after. I've got 6n, I want 19n, I need another 13, so I have to add on 13. 13 times n gives me the 13n extra I need to give me my 19n, and 2 times 13 gives me the 26 I'm after. So k is therefore equal to 13. Part B, hence evaluate the following. Well, you just break that up as the sum from 1 to 40, subtract the sum from 1 to 20 of r plus 1, r plus 3, of r plus 1, r plus 3. Now you have a sum from 1 to n from your previous part. It's this thing here, a 12th n, n plus 1, n plus 2, 3n plus 13. So you've got a sum here, a 12th n, n plus 1, n plus 2, 3n plus 13. So all you've got to do is you've got to substitute 40 in here. So it'd be a 12th, and it gets rather large, but 40, 41, 42, multiplied by 3 times 40, which is 120 plus 13, 133, subtract a 12th, and here our n is 20, so it'd be 20, 21, 22, 3 times 20, 60, plus 13 is 73. So you just tap that in your calculator, and it should all work out for you. So 40 times 41 times 42 times 133, subtract 20 times 21 times 22 times 73, and divided by 12. You should have got 707,210. Let's just check our answers correct by actually doing it with the sum function on the calculator. The sum of x multiplied by x plus 1 multiplied by x plus 3, and you're summing that from 21 up to 40, and tapping that in your calculator, you do indeed get 707,210, and we're done, and we finished all the summing series questions. Thank you for watching.